So this video, we're going to try to talk about how everything we've done so far relates to velocity, acceleration, position, displacement, and how integrals can help us do that. We're going to talk about what we've done in the past, how we can use that, and how integrals might make that easier, or maybe not, but there's more than one way to think about these problems. So we're going to start with what we already know. So if I'm given a velocity, sorry about that. If I'm given a velocity function right here, and it looks like this guy, and it doesn't have a figure. I'm sorry, I'm going to draw a little figure in a second. And this is talking about some particle moving along a horizontal x-axis, s-axis. So this is going to be like s of t, which is what our book uses and what most AP Calculus stuff uses when they talk about the AP exam. We're talking about some interval from 0 to 5. Describe the motion. We're going to talk about that with a graph, and we're also going to talk about that in formula form. So just looking at a graph, and this is not perfect, of velocity, okay, this v of t, which is also ds dt, right? If s is position, the derivative, ds dt is velocity. So if I graph that, and I just did this on my calculator, I start at -8, which is easy to see if you substitute in 0 for t, and then it goes kind of like this. It goes, it has a little inflection point, and then it starts curving up. It becomes concave up, and we can find those values. But this is the velocity. This is the time. So what does this tell you? It tells you on this first little section, velocity is negative. And so if velocity is negative, you're moving to the left on a horizontal line, right? So for this first little part, the particle's moving left. Leftward motion because negative velocity. Now, on this other part here, velocity is positive because it's above the x-axis. So on that part, the particle is moving right on since it's moving horizontally. Here, that's at a 0 velocity. That's where the particle instantaneously stops to change directions. Okay, when a velocity curve crosses over the x-axis, and it has to actually cross, not just touch the x-axis and go back down, it means you actually change directions from left to right, up to down, whatever the case may be, left to right in this situation. Okay, so that's a graph. Now, could we actually use antiderivatives? Because isn't s of t the antiderivative of velocity? So basically, since velocity is the derivative of position, to get position, you take the antiderivative of velocity. So can we do that? It's a little bit more complicated than we've covered because we haven't done use substitution very much. Those of you who've been on Zoom have done it a little bit. But let's see if I can try to explain what it might look like. So if I was going to take that antiderivative, the first part's not so hard. That part's just t to the third over 3 divided by 3 using the power rule. This next part, you have to kind of think of as -8 t plus 1 to the -2. So you're going to end up with a -8. And yes, you add 1. Okay, that's a t. You add 1. I'm going to have to get rid of that stuff off to the side. It's just in the way. And you add 1 to make it up a little bit. Whoops. All right, you add 1 to the exponent, but then you divide by that same exponent. So that becomes a +8, okay? And that comes down, and it's a little more complicated than that, but because that derivative inside of there is just dt, okay? dt is 1. It doesn't matter in this case. So I'm not going to go too crazy, but don't forget your constant of integration plus c, because it could be a whole family of things, and it kind of depends on what that constant of integration is. So you have some function, or a family of functions, because you really don't know what that t is, and I'm going to simplify it a little bit. I'm going to write it like that. That is my position function. So bringing it all back, if I have velocity, I can look at the graph and kind of decide positive velocity, negative velocity, which way is it moving. You can also tell at that graph just looking at the slope, right? Acceleration is the slope of velocity, the derivative of velocity. So all the slopes in this graph over here are positive, right? If you drew a little tangent line, they all have positive slopes. So we have positive acceleration, and it's increasing acceleration over time, right? So it might be decreasing here actually, and then there's an inflection point, and we start increasing. So how about this position function though? How do we find that plus c? Well, until we know one point on the curve, we don't know. So we have a whole family that could be the position, but this velocity might tell us more. And let's go to the next slide to figure out more. So just to review, before we actually go on to the rest of the example, displacement has this whole formula, and we're going to talk about this guy too. Remember that if you take the absolute value, the integral of the absolute value of velocity, it tells you the total distance traveled, versus if you just do the integral on the interval for velocity, it tells you displacement. But I want you to think about that as a whole formula. So this is a fundamental theorem. I mean, that's really just the fundamental theorem of calculus, part one of the fundamental theorem of calculus. And so I want you to think of it as a two-sided formula instead of a one-sided formula for the next thing we do. So this first part here is not what I mean. So if I want to find the total distance traveled during the first 5 seconds, now total distance has to do with that that absolute value. We need to find the integral from 0 to 5. And we're going to do the absolute value of t squared minus 8 over t plus 1 squared. I'm going to make bigger absolute value signs, dt. For now, and because of the nature of what we've done this year and due to the craziness of not being in school, we're going to just use our calculator to do this. I think that a good rule of thumb is we could have done this separately. If we go back to that original slide and looked at our graph, there was a place where it became positive. We'd have to just look at, these two pieces separately and think about what would that look like differently. Since it flipped up, it would be the opposite. So you could do it by hand, but we're not going to do that today. So on your calculator, get that answer. 32.587, I'm going to say units because it didn't say feet or centimeters, but it would be in meters, centimeters, feet, miles, whatever it is. So that's the distance traveled, units, during the first few seconds, 5 seconds to be precise. So you can use integrals to do that. And if we want to then talk a little bit more about finding that whole function for s, for our position, let's talk about having an initial position of the first part in s of 0 equals 9. So just to remember, I'm going to write our s up here. There is simply that I copied that I got from the very first part of this example. And if I want to find that c value before I actually answer the two questions about finding the particle's position, I have to know the position function. But I know one point on my curve. So if I put s of 0 in, I would get this. I mean, I'm just substituting in my 0. And I know that s of 0 is 9. I guess I could have just put that right in, but it's 0 plus then 8 plus c. So guess what my c is? Oh, my c is 1. Okay, so c equals 1. So that is my constant of integration. It tells me my y-intercept rather. It does not, however, tell me my function. So I actually have to go up here and say my function is really plus 1 right here, okay? So this guy right here, I'm going to erase it and say, all right, now I know it's plus 1. So now that I've got my position function, I used antiderivatives to find that position function, so I needed integrals to get it. I can find s of 1 and simply by substituting into my equation. I can find s of 5 simply by plugging into that same equation. And if you do that, and I want you to try it, you should get 5 1/3, or 5.3 repeating obviously, and 44. Now those are positions, so this would be feet or units or whatever. It doesn't really say, we're going to just say units. All right, now there's another way we could do this without actually having to calculate that antiderivative, find that plus c constant of integration, and it involves actually just using that antiderivative. We know that if I'm going to find an antiderivative, and here it's important that you use a point we know. We know that if I take the antiderivative, you should get the position, minus, not an equal. You should get the position of the top limit minus the position of the bottom limit. So if you know one of those, like perhaps s of 0, make sure that's in your integration. And then say you want to know for part A, you want to know the position at 1 second. That's what our antiderivative would look like if I integrated the velocity from 0 to 1. It would give me position, and you'd have to substitute your two limits in. Now, you're going to treat this, like I said, like a whole equation. So this guy is a calculator problem for our thing we know, velocity is that function. I highly suggest you just put this in y1 and be using y1 so you don't have to retype it a whole bunch of times. S1 is what you're looking for, right? That's what this is asking for. The position, that's S of 1. And this guy is S of 5. That's what we found over on the other side a different way. We're looking for that S of 1, but I know S of 0 is 9, so I'm going to substitute that in. So when you do this, this first integral part is a calculator problem, and I got, when I did that in my calculator, -3 2/3. I don't know S of 1, that's what I'm looking for. Then -9, I already knew because that's what they told me it was. And so if I add to both sides, I get 5 1/3. So I added 9 to both sides to get my S of 1. And hey, isn't that exactly the same as I got here? And I didn't actually have to compute the antiderivative, find my C, plug in. It actually might have saved me quite a few steps to just simply use the fundamental theorem using a piece of information I already knew and the piece of information I wanted. So let me tell you or show you a different one. I'm going to use green for part B. So for part B, now I'm going to use 0 again because that's the one I knew from the problem. But you could use 1 because you already know that one. And we're going to go to 5, and I'm going to take the antiderivative of the velocity. Okay, so I'm going to go back to my red formula, and I'm basically substituting in there. That's the fundamental theorem, except I'm using 5 instead of 1. So that should give me S of 5 minus S of 0. Because remember, if I take the antiderivative of velocity, oopsie, I forgot my dt. That's a big important thing. If I take the antiderivative of this velocity function, I should get position, and then put your numbers in, because that's what the fundamental theorem says to do. So basically, I took the antiderivative of velocity, and it gives me the two antiderivatives that you subtract by substituting in the limits. That's exactly what the fundamental theorem says. So now, I did that in my calculator for sanity this time. Yes, in the past, you probably would have been expected to do that by hand, but I got 35 for that integral. I don't know S of 5. That's what I'm looking for. And then my S of 0 was 9 because it was given in the problem. And so when I add that 9 to both sides, I get 44 units, or feet, or whatever it is my S of 5. And that's exactly what I got doing it this other way. So there's more than one way to do it. But this idea that you can set up the fundamental theorem to find the antiderivative is a really important one. And to use one of these that you know when you don't know the other one, it's a really helpful situation. So now what if I take it another step further? So this is not really having to do with this section as much, a little bit, kind of a couple previous sections. But if I wanted to find, if I still have that same thing, and I don't think it says part 2, so ignore the part, but the same thing, we're going to find, I'm going to use the interval, I didn't say it here, I'm going to use 1 to 5, so that's a little bit different. So I'm going to do 1 second to 5 seconds for this page. So if I want to find an average velocity like it asks, okay, on this interval 1 to 5, how do I do that? Well, when we first started, way back in chapter 2, I believe, might have been chapter 3, pardon me, we said we found average velocity by doing delta S over delta T. That's a slope, right? Anytime we're finding an average rate of change, you use the change of one over the change in the other, right? It's just a slope. So in our case, we're going to do S of 5 minus S of 1. Now, over 5 minus 1, right? It's just slope. Now, we already know from that last problem, S of 5 was 44. We know S of 1 is 5 1/3. And 5 minus 1 is just 5 minus 1. So when you do all that math, I got 9 2/3. What does that mean? Remember, this is like feet or units of some sort, whatever unit of distance, and that's time, and we are measured in seconds here. So it's units on top, seconds on bottom, so it's units per second. Now, that's one way to do it. That's the way we did it from the beginning. Notice, we did not use velocity at all to get the average velocity before. However, now, you don't actually have to find that antiderivative because we can find the average velocity using the MVT for integrals. If I'm given a velocity function to find the average velocity, I just do 1 over b minus a v of t dt. So since we had that velocity function, I can do from 1 to 5 seconds, because that's my interval I said, so 5 minus 1, and my velocity function was this guy. Okay, that was given in the problem. Put it in your calculator, 1/4 of whatever that is to be 38 2/3. I did not calculate it separately, honestly. I just divided by 4, but you get 9 2/3. Same dang answer. Units per second. Whatever your units are measured in, feet, miles, whatever. So, you get the same answer. It's the same thing, but look how much faster that was. You didn't have to calculate antiderivatives to get back to find actual position functions. You could just use antiderivatives, just use your calculator, and just get answers. So, MVT can find the average velocity because this sigma integral, sigma notation, allows us to add up all infinite velocities on that interval and divide by those for that 4-second interval, and here you get it. Or you can go back to the other way, but you have to actually go backwards and find that formula, find those two values for the first s and the second s, find the displacement, and then divide by your 4-second interval. One is not better than the other. They are simply different, but you can use integrals to your advantage now. This is going to make the video a little longer, but I'm going to just go for it and talk about this last example then. So how do you use that about this example where you've got a car, initial velocity of 5, okay, initial velocity of 5, and it accelerates at this rate. Now notice that t right there is part of the equation. It's 2.4 t miles per hour per second for 8 seconds. Now it's a weird way to describe acceleration. There's 2 different time versions in there. But how fast is the car going when the 8 seconds are up? How far did the car travel during those 8 seconds? And what's the car's average acceleration? I looked at that last question and go, oh, well, that's easy. I've got the formula for acceleration. I'm going to use the MVT to find the mean value for acceleration. Since acceleration is the function I have, I can simply integrate it on the 0 to 8 seconds. I'm assuming they mean during the 8 seconds, and since I wrote the problem, that's what I mean. I didn't write that. So if the average acceleration on those 8 seconds would be using the mean value theorem. So you need the 1 over b minus a in front because that's a formula to find average values of functions of 2.4 t dt. I literally substituted that into my calculator, although this is certainly an antiderivative you could take because, you get a t squared over 2. And I got 96.8, and then I have that divided by 8 from out front, that 1 over 8 out front, and I got 9.6 miles per hour. Okay, how far did the car travel during those? Now, that's displacement, okay? But to find displacement, I need velocity. So I need to do the antiderivative from 0 to 8 of velocity, but I don't have velocity. I have acceleration. How do I find velocity, if I have an acceleration function? Sounds like I better take an antiderivative. So I'm going to go up here where I have a little more space, and I'm going to say v of t. I'm going to need to find it. And I need to take the antiderivative of acceleration because I need to go backwards and find that. Okay. So I'm looking for a function, so I don't have limits. But I'm going to use those limits to kind of help me. All right, if I take the antiderivative, I get 2.4 t squared divided by 2. So like I said, from down at that bottom example, wouldn't have been so hard to do. plus c. Now, it told me my initial velocity right there in the problem, meaning at time 0, my velocity is 5. So in other words, I have one value I can substitute in to velocity. If I put in 0 to velocity, okay, 2.4 times 0 squared is 0, so I'm just going to put 0. I can actually find my c really easily there. So now I know my velocity function is actually plus 5. It's that 1 point, I'm going to simplify it a little bit. It's 1.2 because divided by 2, 2.4 divided by 2, t squared plus 5. Hallelujah. So now I've got a velocity function. I can actually answer this part B. True? I just actually put it in. I need to go from 0 to 8. I have to have that plus c to be able to do this. You can't do it without it, because now when you take the antiderivative of this, that'll have a 5t involved when you plug in. But for our purposes today, like I said, we're going to use our calculator to help us out. But when I did that in my calculator, 78.6 miles. All right, and I had to go back. I put miles per hour down here, and it asked for average acceleration, and that's a velocity. So I'm sorry, we have to correct that. It's miles per hour per second, which is a weird, it's a weird acceleration unit. So it's miles per hour per second. It's how fast velocity is changing every second this time. So it's how many miles per hour we change every second. On average, the car is increasing its velocity by 9.6 miles per hour every second. So I didn't actually answer part A. So it asked how fast is the car going when the 8 seconds are up. So what are we saying? We need to think back to that same idea with velocity being the antiderivative, or excuse me, displacement being the antiderivative of velocity. Same deal here. Velocity is the antiderivative of acceleration. So if I use the fundamental theorem, I get this whole formula out, and I need my dt. My differential is kind of important. It is a variable. It helps us determine our units. So if I know that the antiderivative of acceleration is velocity, and I've got limits on these, from a to b, the fundamental theorem says if you know the antiderivative, plug the numbers into the antiderivative and subtract. So we're going to use that whole formula just like we did in that last example with displacement. All right, so we're going to use that, but we're going to use, for ours, it says when the 8 seconds are up. So from 0 seconds to 8 seconds. So I really care about this being 0 and 8. So in other words, 8 and 0. We're going to use 8 and 0 because that's what our problem has. So if I take the antiderivative from 0 to 8 of that formula for acceleration, and yes, we're going to use our calculator for this, I'm looking for my velocity at 8 seconds. I know my velocity at 0 seconds is 5, and then we can substitute that in once we find it. So I got 76.8 for that change in velocity is V8 minus 5. So if I add 5 to both sides, you get 81.8 equals the velocity at 8 seconds, which is what it is asking for. So 81.8 miles per hour, because that's what we're measuring velocity in. And there you have it. You can use that fundamental theorem backwards. I like to write it like this. However, I'm going to go back and show you how some people kind of write this a little differently. It's back on a different slide. Theorem way to write velocity as displacement, or the integral of velocity as displacement. Often people will rearrange that by moving this s of a to the other side. So they'll say s of a plus integral from a to b, or conversely, they'll write it a to the integral first. It doesn't really matter, but it just gets confusing as to if that s of a is underneath the integral or within the integral or not, equals s of b. And so sometimes people rearrange that a little bit so it looks like this. It's still the fundamental theorem, just rearranged a little bit, and I find that a little more confusing personally, but you can totally rewrite it. And so that last example that we were just talking about, similarly, you can move this guy over here by writing v of a plus, and then have it move to the other side, plus that integral equals the second value for your velocity. That one's less often used. The one with velocity or some other rate of change is often used first, or most often. And so understand that the fundamental theorem has two sides, and that other side has the antiderivative involved. And so you can use those two values, values of the antiderivative, and if you know one, you can figure out the other as long as you know one. So I think that concludes these, and we're going to keep working on getting everything ready for the AP test. I'm going to post with this video at some point in time. I'm going to post some AP type questions that go along this with this type of problem, as this is often used on the AP test. All right, have a great weekend.